Hi everyone, welcome to another video. In this video, we were going to understand about the attention mechanism and we're going to implement it also using PyTorch and Python. So first, we need to understand what exactly is attention. You probably guys have heard of attention is all you need paper. So in 2017, I believe in 2017, yeah, I think 2017, attention is all you need paper came out and it disrupted everything slowly actually. So right now it's 2025. In today's generation of AI, we are using attention mechanism inside every AI, LLM, or any kind of image generation model also. So in this paper, researchers had introduced a new architecture called transformers. Transformer actually changed everything. After the transformers, we are using transformers only right now, and we have some new architectures like mixers of experts, which is based on transformers and stuff. But the transformer is the basis for that. And why we needed a new architecture, what kind of problem does this attention solve? So let's understand first what limitation does RNNs and LSTM have. So if you don't know about the RNNs and LSTM, RNNs was the architecture where you process each word. So basically you can say tokens sequentially. So every time you, let's suppose there is a sentence, my name is Harsh, you process each word sequentially, my name is Harsh. And then it has a limitation. What's the limitation was that, let's suppose if we have a sentence like this, in India the most common language here is dash, and the model have to predict, or we given the model or a task to predict this next word. Then what happens that RNNs usually forgets the very initial words. So because to actually predict this next word, which could be Hindi, and I think high probability is Hindi, then we need to focus on India. In India, the most common language here is Hindi. But let's suppose if you forget India, if you just focus on the common language here is, then you will confuse yourself. Common language here is where you're talking about, and then you will most likely going to be confused. So that's why RNNs was also confused and was making mistakes, and that was the limitation the attention mechanism and transformer actually solve, because attention mechanism gives weightage to each of the tokens. So India has a weightage. The most common each token will have a weight, and based on this sequence. So let's suppose in this sequence, in this sentence, India will have a high weightage because it contributes more to the sentence to make a prediction. And then language also has a high weightage. I don't think the will have a high weightage. No. Is have a high weightage. No. Certain words will have a high weightage, and that's why, like, that's how it was solved. So this is the architecture of transformer, where you have like a multi-head attention. We will talk about multi-head attention soon. And basically it's kind of architecture where you provide inputs and it predicts the probabilities with what is the next token should be. So the probability of what should be the next token here. And it actually works through attention mechanism, and there are certain layers also. In this video, we were going to only talk about the attention mechanism. I hope to create a new video for the transformer and its implementation. So let's talk about how to compute this attention and how to give weightage to each token. So this is the equation for this, where you have input, you have like a query, key, and value, which are the matrices. So these are basically parameters in neural network, you can say, learnable parameters. And then you basically do the matrix multiplication first, q and k. You transpose the k because then it can only applicable for the matrix multiplication, and then you divide through a constant, which is like to normalize it basically. This is dk is the constant here, and then you do convert. Then you do the softmax to create the probability distribution, and then you again multiply, do the matrix multiplication using the v matrix. So this is the equation for the attention. So let's see the visualization of this self attention. So there are two kind of attention, which is like a self attention and gross attention. Self attention means where you are computing the attention with each other. So let's suppose you have a sequence and then you are computing the attention of each of the tokens by itself. And then cross attention is with one sequence and the other sequence, which is basically used in other which I'll talk about in other videos possibly. And the thing with it, you can see here, like you will find like a different weightage to its own sequences. So law has this higher weightage, which is like a darker line to its law in the. And similar to like that, I'm not sure it is exactly coming from the trained model, but you can just visualize this thing, and then you can just like give yourself as an imagination. That's how it works. It gives weightage to each of the tokens of in the sequence. So this was the visualization of the self attention. Now let's learn the multi-head attention architecture. So as we have seen in the transformer architecture, we have multi-head attention. So why do we need multi-head attention? Like if we have this attention, we can calculate this like that. Why do we need a multiple heads kind of thing? So this kind of thing is very efficient from the RNN's perspective. So in RNNs, we used to calculate sequentially and stuff like that. Here we can like compute all the attention scores in one go in a sequence. We don't need to like do one processing at a time, but still we need more, like to make it more advanced or make it more better. So let's suppose if we have a dimension of 512, then we are dividing into 4 heads. It will be distributed equally. So each head have 128 dimension, 128, 120, 120, and each head will have like QKV. This is a good thing because the more heads we have, the more parameters we have, the more different Q, K, and V value we'll have, and then they will learn differently from this. So each head will have a different perspective kind of thing, and with more parameters. Then that's how you make the model more complex, and to increase the number of parameters where you have a more different complexity, which contributes to more better outputs. And then you do the computation parallelly. So all the QKV and all the heads basically going to be computed parallelly, and then in the end you combine all of this, and then you move forward in the forward pass. So this was about the attention. Let's implement this so you will understand much better. The best way to learn anything is to build it from scratch, and yeah, let's go. So let's implement the multi-head attention. For that we need to import some of the required libraries, which is math, torch, torch.nn, and functional. We need to import functional as f. Then what we need to do is like we need to build a class. Then we will create a class called multi-head attention, and then dot module as an inheritance, and then we have to construct a constructor where we will pass some of the parameters like number of heads and then dimension dmbed. Okay. Call the super nice. embed. Okay. Although we don't need this thing, possibly we just need cell dot. We need as a make this as a property here. Then we need to create a in projection layer and a out projection layer. So in projection layer is where you have input embedding, where the input embedding goes to in projection layer for the in projection layer, and then we need to create a in projection layer and out projection layer. So in projection layer where the input comes from it, and then after going through the in projection layer we will do the attention process, and then in the end after we will do the attention process we will inject through the out projection layer, then it will go through another block of the transformer. So it's like that. So self dot in projection, which is linear, it will be dimension. So the input for this will be exactly the what we have as input embedding dimension. So d embedding, and now we know that it will come with the same dimension of the input, but we are creating three things here, which is QKV. So we can extract QKV from it. So 3 into dimension as an output for this linear. And then out projection. After doing the attention, as we have seen in the multi-head architecture, that we will combine all the outputs of heads, and then it is the same, the output will be the same as the dimension what we have in the input embedding. So we just need to project out for the another block. So de-embedding and then de-embedding. Then we can just define dimension of heads, which is going to be, means what will the dimension of each head. So we can just like do this, de-embed divided by number of heads. It will be the dimension of each heads. Now it's our constructor is completed. We need to create a forward pass. So guys, for some technical reason I have to switch off my camera, and so let's go forward with the forward method. And here we have to do is so we get the x, let's do the x, define the shape of what will be the x shape. So here we have batch, sequence, and features, right? Then we can input shape is x dot shape. This will be the input shape. We can just extract batch from here, sequence length from here, the embed from here, shape, and interim shape, which is what shape we want to do, because we need to reshape our this input to some different shape to make the attention process work. We need to divide this into a number of heads. That's why we need to reshape our input. So it will be batch and sequence length, self dot n head, and de-embed. So here in the shape of -1, index of -2, we got the number of heads. So earlier we had this, now we have number of heads and then d-dimension, which will be equals to self dot n head divided de-embed divided by self.heads. Okay, so let's do the introjection here with x. So it will going to be like this. So b batch size, sequence length, and f into 3. Features will be the 3 times of it. So then we can extract the QKV from this. How can we extract it? We need to chunk it. So there is a function in PyTorch, chunking. So this will be 3 times of okay, let's do the first, this QKV. QKV are the matrices, and then c dot chunk 3 dimension minus 1. So in the last dimension we will chunk 3 matrices. So basically we will have Q and KV. So what I was writing, this thing, 3 multiplied by BS and F. So Q equals to Q dot view interim shape. Now the Q will have this shape, but what we need is this shape to make our attention work, which is batch size, and heads will be there. So then we will have sequence length. So sequence length, and then f divided by h, which is the dimension. So this is the interim shape, and then what we can do to make our head go from here to here, the side, we can transpose it. Similarly too, we can just do for the K and B. Then what we can do is weight. As we know the formula of the attention, which is, let's go and review this again. This is the formula, right? So what we are doing is like we multiplying it, doing the matrix multiplication, and then dividing that with constant, and then softmax, and then doing again the matrix multiplication. So this is the same thing we will implement here, and for that we have to do the matrix multiplication, Q and K. So Q, and then how we do the matrix multiplication is add the rate, and then K dot transpose -1 -2. So it will have the required shape to do the matrix multiplication, and then the result we will store it in a weight variable. And then we need to do is like we need to divide it by a constant, which is these self dot dimension of heads. So here dk is the dimension of heads, basically dk is the number of heads here. Got it? Awesome. So basically our model is in autoregressive state, and it is predicting each token at each time step. So we need to make sure that we don't give the whole sentence and then model is predicting those, because it will have the information for the future as well. So let's suppose if the time step is there in India, so the model needs to only show the end thing. We want to make sure that the model only have the past data, and based on the past data it can predict the future one. So torch.1 like will create a boolean upper triangular mask where the upper right part is so here it will be look like this, where the first time step you have given the first token information, and others are hidden with the -infinity, and similar to like that as the model progress and do the autoregressive process, it will going to have more information and stuff. So the model process it step by step. In predicts India, and then in India when after in India, it should need to predict this thing, and it will like learn like this. So this is called semi-supervised learning also, where like we don't have any kind of labels, but we generated labels by just with just feature token. So the label for this sequence is India, and then now for the next time step, the label for this is this comma, and then for this is this, and then similarly to do the autoregressive step. Okay, so I hope you got it. Now let's build. So what we just do is mask equals to torch dot once like weight the type equals to torch dot bool dot try and one, and then weight dot mask fill and then we will fill that with infinity minus infinity. Then we will do the softmax. So why we are doing this minus infinity, I think I've written in my blog also, is so we are also applying mask the weight, but why we are applying mask? The purpose of applying mask is implement casual attention, which is autoregressive. The mask replaces future position with minus infinity, causing softmax to assign them non-zero weight. So when we will apply the softmax, this weight, it will apply to assign them as a non-zero weight, right? If you know the softmax, you know like how it works. This ensures the model only attends to past tokens during autoregressive generation. Got it. So then we will do, so output it, which is weight matrix multiplication with V. Then we will transpose again output, because we need to make it into a basically we are backing our initial shape. So and then reshape it input shape, so it will back to our input shape here. Then output equals to self dot out projection layer, which is the output. So you must have noticed that what I was talking key, that we need to concatenate or basically add all the outputs from the different heads, but here we are just doing it in a different way. But you can also implement in a concatenation way, where you have outputs and then you just concatenate. Here we are just like reshaping things again and again. Return output, and so this is what the multi-head attention is. I hope you guys understood how to implement and how it works. If you like this video, please subscribe the channel and stay tuned for the next videos. Bye.